Good morning, class. We are looking at chapter 2, linear, absolute, and quadratic functions. Here's section 2.5, complex numbers. So we've covered linear functions, graphs of linear functions, modeling with linear functions, absolute value functions, and now complex numbers. The objectives are add and subtract complex numbers, multiply and divide complex numbers, simplify powers of I, recognize a complex number, addition and subtraction, multiplication, conjugate and division, powers of I. Recall rectangular coordinate system linear equations. We want to look at it, reminding you of the distance formula. D is square root of x up to minus x of 1 quantity squared plus y sub 2 minus y sub 1 quantity squared, and the midpoint. Add up the coordinates, divide by 2, x sub 1 plus x sub 2 divided by 2, y sub 1 plus y sub 2 divided by 2, when you have 2 points with coordinates given. This is 1 point. This is the second one. Proportion, if A over B equals C over D, then AD equals BC, and of course the denominators can't be 0. M rise over run, delta y over delta x, so y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Lines in standard form, we have ax plus by equals c, slope intercept form y equals mx plus b, and point slope y minus y1 equals m times x minus x sub 1. Vertical line, x equals a, the slope is undefined, x intercept at a0. Horizontal line, y equals b, slope is 0, y intercept at 0b. Two lines are parallel if they have equal slopes, different y intercepts. Two lines are perpendicular if the product of their slope is -1, or one slope is the negative reciprocal of the other. Complex numbers. An imaginary number is a number such as square root of -5. It is called imaginary because when imaginary numbers were first introduced, many mathematicians refused to believe they existed. The imaginary unit, I, equals square root of -1. Square root of a negative number for any positive real number n, square root of negative n is the square root of -1 times n. That square root of -1 must be replaced by I. Complex numbers are numbers of the form a plus bi. A and b are real numbers, and I is the imaginary unit. Every real number and every imaginary number are also complex numbers. Real part is A, imaginary part is B, and a standard form of a complex number is A plus BI. So we have whole numbers, integers, rational numbers, irrational numbers, real numbers, non-real numbers, and all of them together is complex numbers. So we also have natural numbers. Let me just write this for you. So natural numbers in 1, 2, 3, 2. This is called the set of positive integers or counting numbers. Whole numbers, we add 0. Integers, we look at the negative side also, and we add to it. In other words, 0, 1, 2 to infinity, and -1, -2 to infinity. Rational numbers, anything that we can put into form of a fraction, where the top and the bottom are integers. X such that x equals p over q, and p and q belong to the set called integers, meaning you can write it in a fractional format. The top and the bottom must be integers. So for example, decimals and repeating decimals are also considered rational numbers. But something like pi, it's 3.14159, and it continues indefinitely. It's not a rational number. And then non-real numbers are in the form of a plus bi, where a is the real part, b is the imaginary part. If a is 0, becomes a pure imaginary, and all of them together, we call them complex numbers. So let me actually let me just clean this up and just look at the rest. All 4 operations can be performed on complex numbers. To do so, use the definition I equals square root of -1 and I squared equals -1. We will look at powers of I later on. The union of the set of all imaginary numbers and the set of all real numbers is the set of all complex numbers. So complex numbers contain all those numbers, real as well as imaginary. Write each complex number in standard form of a plus bi, where I is defined as square root of -1. So clearly, this is -1 times 16, and this -1 must be replaced by I. 16 comes out as 4, so we write 4i. You don't want to have a negative under the radical, so that one is replaced by I outside the radical. So you put I squared of 21 or square root of 21i. The reason sometimes they avoid writing that, because sometimes students make a mistake. They think is I is under the radical, which is absolutely not. Okay, so make sure you recognize that's outside. Now, -32 under the radical. The negative sign, you can get rid of it and put an I outside. 32 is 16 times 2. 16 is 4. There are 2 ways to write it. You can write 4 square root of 2i or 4i square root of 2. Again, bear in mind, I is outside the radical sign. That's why they put it in between, to make sure everybody can recognize that's not under the radical. Square root of negative 9 is the product of negative 1 and 9 inside. Negative 1 under the radical is replaced by I, and this is 3, so 3I. This negative outside remains. This negative inside is replaced with I outside. For the 8, it's the product of 16 and 3. So this is negative, this is I, and this is 4. So you can write it in this format, minus 4I squared of 3, or you can write minus 4 square root of 3. Make sure the I is outside. Either way is fine. Now, one thing I want to tell you about 48. You want to take the big chunk that is square, a complete square, out, and you can recognize it 16 times 3. But if you don't, if the number is larger, you can always do prime factoring. So 48, remember the prime numbers. 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. So the first one is 2, and it's divisible by it. 24 is 2. 12 divided by 2. 6 divided by 2. 3, you can't divide by 2 anymore. Now you divide by 3, you hit 1, and you're done. So I want to write here that square root of 48, therefore, is square root of 2 to the power of 4 times 3. And 2 to the power of 4 or 16 comes out as 2 squared. Or just in case, if this number is large, you can do prime factoring as follows. Add and subtract complex numbers. We add complex numbers just like we add polynomials by combining like terms. Remember, a plus b I square root of negative 1. The complex numbers obey the commutative, associative, and distributive laws. Thus, we can add and subtract them as we do binomials. So you want to add this because it's a plus sign. Remember, if you have a parenthesis, you have to distribute, but it's a plus sign, so nothing changes. So notice you can add the numbers 9, negative 6, 18, and the imaginary parts 15i and negative 2i. So these three numbers, 9 and negative 6, positive 3 and 18 is 21. 15 minus 2, 13i. So it's that simple. Just add up like terms. That's all you have to do. What about it here? Again, I see a plus sign. So add these two numbers. And that gives you negative 3. Add these two. And that gives you negative 7i. However, in this case, before you do that, you have to distribute the negative because things start changing. The sign changes. This remains unchanged. This is negative 4. This is plus 12i. So you combine these two and you combine these two. So you say negative 3 and negative 4 is negative 7. These two add up to 16i and we're done. So just add the way you would add like terms. Think about like terms, everybody, and it really makes it easy to do. multiply complex numbers, reminding you that complex numbers are in the form of a plus bi. I by definition is square root of negative 1. We want to multiply these two. So number one, change all imaginary numbers to bi. So in case you have a square root and negative sign. Then multiply the complex numbers as you would multiply polynomials. Substitute negative 1 for each I squared. Combine the real parts and the imaginary parts. Write the answer in standard form, a plus bi form, which is the standard form. So negative and positive, negative 32i squared. And since I squared is negative 1, the result is positive 32. It should be pretty straightforward, everybody. Let's do this. We are going to distribute. We get 18i minus 12i squared. I squared is replaced with negative 1. So this is negative 1. So you get 18i plus 12. You can leave it like that, but in the form of a plus bi, we put the 12 first. So this is a plus bi, in case if you want to write it in that format. We are going to FOIL. So 9 times 3, 27, plus 9i minus 12i minus 4i squared. So just the foiling. And quickly, I squared is replaced with negative 1. So times negative 4 becomes positive 4. And (27) and 4 can be added to 31. 9i minus 12i, they can be added to negative 3i. And it's in the form of a plus bi. By the way, please notice that b is negative 3 in case. We can do the foiling again, but the easy way out is to remember the identities. Recall a plus b times a minus b was a squared minus b squared. Everybody remembers that. So if we have a plus bi times a minus bi, we get a squared minus b squared I squared, which is a squared plus b squared. Therefore, RT becomes 7 squared plus 2 squared. Again, knowing identities. Otherwise, you have to FOIL and then simplify by combining like terms. This is 49, this is 4, and they add up to 53. multiply. And it's important to be careful with a case like this, everybody. In order to multiply those, you have to change them to 2i and 3i in order. The result is 6i squared, which is minus 6. In other words, just for the real numbers, you can't assume that I can multiply these two numbers. I get 36, and then square root of 36 is 6. So you can't assume this, everybody. So I hope everybody's okay with this. And again, not mixing things up. So what do we do here? Square root of 2 times I, or I times square root of 2. Square root of 10 times I, or I times square root of 10. So we have to get rid of the negative sign by changing it to I. These two result in I squared. This 2 is square root of 20. Now, we know 20 is the product of 4 and 5. Okay. So 4 comes out as 2, 5 remains. I squared is changed to a negative sign. Negative 2 square root of 5. Part B, let's distribute. We get 10i plus 6i squared. I squared is replaced by negative 1, so this is minus 6. And you can leave it like that, but to put it in the form of a plus bi, we put the real number first. A is negative 6, b is positive. Part C, we are going to FOIL. Which means we're going to say 2 times 4 is 8. 2 times negative 3i is negative 6i. I times 4 is plus 4i. I times negative 3i is negative 3i squared. I squared is negative 1. So negative 3i squared is plus 3. And so we have 8 minus 2i plus 3. These two combine to give us 11 minus 2i. The conjugate of a complex number a plus bi is a minus bi. It's called the complex conjugate. So for example, if I want to find the complex conjugate here, 3 plus 7i becomes 3 minus 7i. 1 minus I squared of 3 becomes 1 plus I squared of 3. 2i, recognize it as 0 plus 2i, so it becomes 0 minus 2i, or simply negative 2i. Again, if 2i doesn't give you enough information, change it to 0 plus 2i so you see that. So negating the imaginary part, whatever this imaginary part is, negate that, write the opposite of that. To divide complex numbers, change all imaginary numbers to BI form. Multiply both the numerator and the denominator by the conjugate of the denominator. Write the answer in A plus BI form. What do we mean by that? Let's look at some examples. If you happen to have denominator as a purely imaginary, just all you have to do, multiply the top and the bottom by I, it will fix the problem. Again, if the denominator is purely imaginary. So the numerator is 7i, the bottom is 3i squared. Which is -3, and you write it in this format. The reason you want to write it in this format, because please, you need to understand B is -7/3, and by the way, A is 0. We don't have a real part here. So for this one, you can cut them into 2 fractions. It will do the job. Or you can multiply by I over I. So the numerator is 9i plus I squared, and the bottom is I squared. And we are going to replace each I squared by -1. So that means this gives us -9i. This will give us +1. We put the 1 first to put it in the form of A plus BI. We are going to multiply by the complex conjugate of the denominator and divide by it. So 5 minus I, you're going to multiply and divide by 5 plus I. This expression is equal to 1. This expression equals 1, and that's okay then. Okay. So the numerator we do FOILing. At the bottom is just 5 squared plus 1 squared. So this one, 3 times 5, 15. At 3i and 25i. We can do this in one shot. So the product of these two and the product of these two. So you have 25i, 3i, they add up to 28i, and then 5i squared. I hope you can do the FOILing pretty fast by now. We've seen it many times before. And so 5i squared is replaced with -5. And you combine it with 15 to get 10, and the bottom is 26. So we have 10 plus 28i divided by 26. We make up 2 fractions, and we simplify each one. As you can see, they are both divisible by 2, the top and the bottom, and we get 5 over 13 plus 14 over 13i. So this is A plus BI. The reason you want to separate them, because you want to know what is A and B. If you're asked, you should be able to answer it easily. Okay. Let's look at powers of I, we want to simplify the following. So we start with I is square root of -1, I squared is -1, I cubed is -I to the power of 4 is 1, and the successive powers of I rotate through the four values of I, -1, I, and 1. I want to quickly show you this one. So, of course, we know I is square root of -1, I squared is -1, I cubed is I squared times I. That makes it minus I to the power of 4. There are two ways to write it. One easy way would be I squared to the second power, -1 squared, making it +1. That's why we have those. And we should know that. Now, they give you this. I to the power of n is I if n is 1, 5, 9. -1 is 2, 6, 10, whatever. -I if it's 3, 7, 11. And 1 if it's 4, 8, 12, something. I don't like this. I'm going to show you the easiest way to figure this out. You don't have to memorize any of it. What you do, you divide the exponent by 4. In this case, it gives you 10 with the remainder 0. So that is the same as I to the power of 0, because I to the power of 4 is 1. I to the power of 40 or 400 or 4,000 or any number divisible by 4 is 1. So you can write this in the following manner: I to the power of 4 to the power of 10, 1 to the power of 10 or 1. But like I said, this is the fastest way. I'm going to show you how they might approach part B, and I'm going to show you my way. So 33 is, and the same concept that I said, divisible by 4. When you divide it by 4, you get 8 with the remainder 1. So the answer is I. So I would divide this number, 33, by 4. The answer is 8 with the remainder 1. I'm interested. So the answer is this: I to the power of 1, which is I. That's all you have to do. Okay. I'm going to give you a couple more examples so you see how easy you can figure things out. Okay. Divide by 4, keep the remainder. So fastest way would be to divide the exponent by 4, keep the remainder. 2002. When you divide by 4, I hope you know that 2000 is divisible by 4. The remainder is 2. You don't even have to know what's the quotient. You just want the remainder. So 2002 divided by 4, remainder is 2. So this is the same as I squared. And of course, I squared, you know, it's -1. And you're done. Let's look at I to the power of 43. 43 divided by 4. The remainder is 3. And so I to the power of 43 is I cubed, which makes it -I. I to the power of 164. Divide by 4. Remainder is 0. So this is I to the power of 0, which is 1. Okay. Or in short, if the remainder is 0, the answer is 1. Okay. Now, if they said simplify, divide, write it in standard form, they all mean the same thing. You have to answer as A plus BI. So this is 5i, this is 3i. So 2 plus 5i, 4 minus 3i. That's the first thing you do. And now the methodology is to multiply and divide by the complex conjugate of the denominator. The top, we FOIL, and we say 2 times 4 is 8, 2 times 3i, 6i, 5i times 4, 20, so 26i plus 15i squared, 4 squared plus 3 squared at the bottom. I'm assuming nobody has any problem with foiling class, okay? Okay, so 2 times 4 is 8. 2 times 3i, 6i, 5 times 5i times 4i, 20i. They add up to 26i, 15i squared, and we replace it with negative 15. And so 8 and negative 15, they add up to negative 7. 6, let me just write this. 16 and 9, they add up to 25. You make up two fractions. You get negative 7 over 25 plus 26 over 25i. So therefore, this is A plus BI. So A is negative 7 over 25 and B is 26 over 25. So let's look at this question. And the question is x equals 2 minus I a solution of this equation x squared minus 4x plus 5 equals 0? Well, you have to check, meaning you have to plug in. So we are going to replace the x with 2 minus I. So we do that. 2 minus I squared minus 4 times 2 minus I plus 5. We are checking to see if we get 0. Okay. Now this is 4 minus 4i plus I squared. This is minus 8 plus 4i plus 5. I'm assuming you have no problem with squaring an expression and so forth. So notice what happens here. 4i, negative 4i cancel each other. This number becomes minus 1. Now 4 with negative 1 is positive 3. With positive 5 is positive 8. With negative 8 is 0. And the answer is yes. Because they do add up to 0, the answer is yes. This is a solution. Add or subtract and simplify. Because this has a plus sign, the sign doesn't change. You don't have to distribute. Just understand put 3 and 7 together, 2i and 8i together. Because you're adding like terms, you can do it in one or two shots. This is 10, this is 10i, and we are done. A plus bi. It's fairly simple. Because this one has a negative sign, we have to distribute. And we're going to write 10 minus 2i minus 9 minus I. Ten and negative 9 go together. Negative 2i and negative I go together. And we get 1 minus 3i. So it's pretty straightforward, everyone. All right, again, divide and simplify to the form a plus bi. Please understand, divide or simplify or put it in standard form mean the same thing. When we have I in the denominator or multiples of that, just multiply and divide by I. That is the fastest and easiest way to deal with this. So the denominator clearly is I squared. This one is 3i and this one is 2i squared. So this remains, this changes to negative 2, this changes to negative 1. And the result is that they change signs. So this becomes negative, this becomes positive. And this is the answer, and you can leave it like that, but this one is in the form of a plus bi, a plus bi, where a is 2 and b is negative 3. And I can't emphasize this enough, everybody. Okay. But because the denominator has, in essence, binomial two terms, okay, you multiply by the conjugate 2 plus 3i and divide by it, and this expression is equal to 1, and that's acceptable. And the bottom is easy, just a squared plus b squared, that means 2 squared plus 3 squared. And the numerator, we do the foiling. So let's do the foiling for the top. We get 4 times 2 is 8, 4 times 3i is 12i, I times 2 is 2i, I times 3i is 3i squared. Now the denominator, it's really 4 plus 9, but anyways, 2 squared is 4 minus 9i squared, which makes it plus 9. So this is a negative 3, and this is a positive 9. And so these two add up to 13. These two add up to 5. And these two add up to 14i. We're done. If you left it as that, it's fine. However, the reason I like to separate them, so if somebody says, what is A? Clearly, it's not 5. It's 5 over 13. And B is 14 over 13. So you can see the standard form of a plus bi. That's truly helpful. I want to look at one more thing that we will look at it with more details later. Okay, but just to give you an idea, the concept of a complex plane. A complex number z equals x plus y times I instead of a plus bi. That's the same concept. X and y are real numbers. I is square root of minus 1. And it's an imaginary number. The magnitude or modulus of a z is the distance from the origin to the point x comma y. And it's equal, that we write it like, looks like an absolute value. That's modulus, or the magnitude of z, square root of x squared plus y squared, or r. We will discuss this with more details, okay, later, but for now. Here's a complex plane, the x-axis or the real line, the y-axis or the imaginary axis. So here's the angle theta, and again, this is counterclockwise and positive. Here's r. Z has the formula, instead of a plus bi, we say x plus iy, okay. And then z bar, okay, or the conjugate is x minus iy. So this is in the first quadrant. This is in the fourth quadrant. And again, here's the real axis. Here's the imaginary axis. The modulus of z, as we said, r is the square root of x squared plus y squared, or z bar. This is called z bar, or the conjugate, the product of the two under the radical. X is r cosine theta, y is r sine theta. Okay. If r is greater than or equal to 0 and theta is between 0 and 2 pi, complex numbers in polar form. Again, we discuss it towards the end. Z is x plus y I, r cosine theta plus I, r sine theta, short r cis theta. Just to get you familiar with the concept, you don't have to worry about it too much. And tan theta is y over x, or sine over cosine. X represents cosine, y represents sine. So here's a simple example. Just understanding the complex plane, we want to plot the complex numbers 2 plus 2i and 1 minus 2i. So for plotting this, if we have the real axis and imaginary axis, look at these numbers and just write this. Think about 2 comma 2 as far as basic rectangular coordinate system is concerned. That means 2 to the right, 2 to the top, and it goes somewhere there. So that would be the point. Whereas for this one, you would say 1 comma negative 2, and that means 1 to the right and 2 down, so somewhere here. That's all I want you to know, that when it comes to a complex number, how do I plot points? That's all you have to do. The rest we'll discuss with more details when we look at trigonometry.